A vision model that aces captions can still fail tables and charts. LMMS-Eval runs reproducible OmniDocBench and ChartQA tasks so you can choose on the workload that matters. You'll evaluate vision language models on ChartQA and OmniDocBench with LMMS-Eval, measure per sample differences, and select the stronger model. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Multimodal benchmarking matters because different visual tasks exercise different skills. One model might write a lovely caption, but miss a table cell, mangle a chart label, or ignore a numeric instruction. Engineers need a fair, repeatable way to compare models on the exact tasks they care about, not just leaderboard numbers. LMMS-Eval packages the task definitions, prompts, and metrics so teams can run the same evaluation reliably. The core idea is straightforward. Run the same prompts against two model backends, score the outputs with the task metrics, then inspect per sample disagreements to see where one model wins and the other fails. That tells you whether a model is good enough for chart reading, document QA, or both. The upside is reproducibility and per sample visibility. The downside is that thorough runs cost more compute, so start small. We will build a compact experiment that confirms task availability, loads the task configs, runs a short smoke evaluation of a smaller checkpoint, runs a larger checkpoint, then compares per sample outputs, and writes a tiny baseline report. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we check that the environment actually exposes the two benchmarks we need, so we do a light registry scan before we start. This snippet checks whether the two target benchmarks are available in LMMS-Eval. Engineers often lose reproducibility before the model even runs because task names drift or a local environment is missing a benchmark. Task Manager scans the installed LMMS-Eval task registry without downloading datasets, and eval tasks keeps only ChartQA and OmniDocBench when they are present. That gives the rest of the tutorial one shared task list instead of hand-typed strings in every run. The visible output shows the benchmark names that this environment can actually evaluate. Finding the tasks is necessary, but we still need the task objects that carry scoring rules and output expectations. This example loads the benchmark definitions that will control scoring. A model comparison is only meaningful when both models face the same prompts, output type, and metric definitions. So getTaskDict turns eval tasks into concrete LMMS-Eval task objects. The task config.metricListCount is a quick sanity check that scoring rules exist, while task.config.outputType confirms that these are generation-style evaluations rather than a different request type. This call can trigger dataset setup, so it is the first step that may touch cached benchmark data. The output shows which task output modes and metric specs LMMS-Eval found. With tasks prepared, run a tiny end-to-end pass to confirm your model backend, prompt handling, and metric hooks all work together. This code runs the first real LMMS-Eval evaluation pass with simple evaluate. The point is not to claim a leaderboard result yet. It is to prove the full path from model backend to benchmark metrics works on a tiny, repeatable slice. Model A-args selects the Qwen 2.5 VL checkpoint. Limit equals 2 keeps the run short for experimentation, and log samples equals true preserves per example outputs for later debugging. Increasing limit makes the estimate more representative, but also increases runtime and data processed. The output shows which benchmark result blocks were produced by the run. The smoke run proved the pipeline. Now run the second model and align the per sample records so you can compare answers side by side. This snippet puts two model runs side by side at the sample level. Aggregate scores can hide the cases that matter most, especially on charts and document layouts, where one answer may reveal an OCR, table, or reasoning failure. The second simple evaluate call runs the larger checkpoint with the same eval tasks, limit, and log samples setting. Then, samples A and samples B compare filtered rests, which is the scored model response after LMMS-Eval filtering. The code aligns examples by ID and inspects where the visible responses differ. The output shows how many shared examples were inspected and how often the visible answers differed. After you can see differences, capture a compact baseline and save it so the experiment is reproducible and reviewable. This code turns the experiment into a small tracked baseline instead of a one-off demo. The score function gathers numeric metrics from the LMMS-Eval Run A and Run B result dictionaries, then averages them into a compact comparison value. That average is a lightweight tutorial summary, not a replacement for reading each benchmark metric and sample log. Card records the task list, model scores, and selected winner, and path.write text saves it as a JSON artifact for review or CI storage. The output shows the chosen baseline model and the score that was written to disk. This toy flow maps easily to a production check. Replace limit with a full dataset run, stream results into your model registry, and surface the per sample disagreements in a lightweight dashboard for QA reviewers. 3 quick takeaways. LMMS-Eval gives you reproducible task definitions and metrics that teams can share. Use it when you need to compare vision language models on chart reading or document QA, not just image captions. And remember, short runs are for validation. A full evaluation needs many more samples and more time. A sensible next step is to increase limit to 200 and run the same experiment on the full ChartQA split. Then inspect the most frequent disagreement cases to tune prompt templates and OCR pre-processing. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.